Hey there and welcome. Today, we're going to talk about something absolutely fundamental to robotics. We're going to teach a robot how to, well, not exactly see, but how to understand its own position and which way it's pointing in 3D space. This is the absolute foundation for everything a robot does. So, yeah, let's dive right in.
Just look at these incredible machines. You've got this super complex robotic arm, a crazy agile drone. They seem to move with such purpose, right? So much precision. But what if I told you that all of this complexity, all that intense math, boils down to the robot just asking itself one single question over and over again? And that's the question: where am I and which way am I facing? Seriously, that's it. So in this explainer, we're going to break down exactly how a robot formulates the answer to that, all using the language of mathematics. Okay, so to get started, a robot needs a point of view. Actually, scratch that. It really needs multiple points of view. And in the world of robotics, we call these frames of reference.
This is a great way to wrap your head around it. Imagine you're on a train, right? You've got a cup of coffee sitting on the table. To you, it's perfectly still. That's your local frame of reference. But what about someone standing on the platform watching the train zip by? To them, that same coffee cup is moving at like 100 kilometers an hour. That's the global or world frame. And for a robot to do anything useful, it has to get a handle on both. So here's the key takeaway. A robot absolutely needs both of these frames. It uses that global frame, you can just think of it as a fixed map of the room, to know where it is in the grand scheme of things. But it also uses its own local frame, which is kind of attached to its body, to understand things right around it. You know, stuff like my hand is half a meter in front of my face. It needs both to function. So how do we actually write this down in math? Well, it's surprisingly simple. Whether we're talking about a little 2D car on a flat grid or a full-on 3D drone buzzing around a room, we use this little package of numbers called a vector. For the car, it's just an X and a Y position. For the drone, we just tack on a Z for the height. That vector? That's the basic language for telling something where it is. Now, to make sure everyone's on the same page and avoid total chaos, engineers came up with a standard. It's called the right-hand rule. You can do it right now. Stick out your right hand, point your thumb up, say along the Z-axis. See how your fingers curl? That direction is the positive direction of rotation. It's a super simple trick, but it means that every roboticist and every robot in the world agrees on which way is up and which way is a positive spin. Super important. Okay, so our robot now knows where it is. Location. Check. But that's literally only half the problem. Now we need a way to describe which direction it's facing. And trust me, this is where things get really, really interesting.
Probably the most intuitive way to think about rotation is something called Euler Angles. Just picture an airplane. When it tilts its wings side to side, that's roll. That's rotation around its front-to-back x-axis. When it points its nose up or down, that's pitch. That's around the wing-to-wing y-axis. And when it turns left or right, that's a yaw, rotating around the vertical z-axis. Roll, pitch, yaw. Seems pretty straightforward, right?
I mean, it seems perfect. Just 3 numbers, and you can describe any possible orientation in space. But there's a hidden, fatal flaw. Seriously. A catastrophic little math problem hiding in this simple system that can cause a robot to just completely lock up. And here it is. This is the problem. It's called Gimbal Lock. Look, if you take that airplane and pitch its nose straight up, 90 degrees, suddenly the axis you use for roll and the axis you use for yaw are pointing in the exact same direction. They're doing the same job. You've basically lost one of your controls, or what we call a degree of freedom. The math just breaks down. It can't tell the difference between rolling and yawing anymore. And the robot, it just gets stuck.
So, yeah, having our multi-million-dollar robots randomly seize up is, not great. So, of course, engineers came up with some much smarter, glitch-free solutions to handle all this spinning.
One of the first big ideas is based on something called Euler's theorem. It says, hey, forget about doing 3 separate little rotations. Any orientation you can possibly imagine can be reached with just one single rotation around one single axis. The best way to picture it is like stabbing a marshmallow with a skewer, right? You can stick the skewer in at any angle you want, and then you just twist it. One axis, the skewer, and one angle, the twist. That's all you need.
But let's be real. The modern industry standard, the real hero of our rotation story, is something called a quaternion. Now, don't let the name scare you. On a high level, you can just think of them as complex numbers that went to the gym and got totally jacked. They use 4 numbers to represent a 3D rotation, and they do it in a way that's, well, it's beautiful mathematically. And, most importantly, they are completely 100% immune to Gimbal Lock. And wow, this image just says it all, doesn't it?
On the left, that tangled mess, that's what happens when you hit that gimbal lock problem. It's broken, it's unpredictable. And on the right, that's the Quaternion path. It's smooth, it's stable, it's totally unrestricted. For a robot, that's the difference between moving like it's having a seizure and moving with fluid, reliable precision.
Okay, let's take a breath. We now have a way to describe a robot's location. We call that translation. And we have a good way to describe its orientation. That's rotation. But in the real world, robots are doing both at the same time. They're moving and spinning. So, how on earth do we combine the two?
Well, if you just try to mush them together, it gets ugly fast. See, rotation is basically a multiplication operation, but translation is an addition. And if you try to chain a few moves together, like move forward, then turn, then move again, the algebra just explodes into this horrible mess you see on the screen. Now imagine trying to calculate that for a robot arm that has 6 or 7 joints. No way.
So to fix this mess, engineers came up with a really clever hack. I mean, it's brilliant. It's called a Homogeneous Transformation Matrix. What they did was they added one little extra dimension to the math, just a phantom dimension. And that allowed them to package the 3x3 rotation matrix and the 3D translation vector into one single, clean 4x4 matrix. And the magic is, now every single operation, rotating, moving, whatever, it's all just simple matrix multiplication. So elegant.
And what this beautiful matrix describes is something we call rigid motion. This combination of rotation and translation together gets a special name, a pose. It's the full description of where an object is and how it's oriented. And this one matrix can describe the entire change, taking an object from its starting pose to its final pose in one single, clean calculation.
But hold on, if these big 4x4 matrices are so perfect and clean, why is it that when you look at modern robotic systems, like ROS, the robot operating system, they often don't use them? Instead, they just keep the quaternion for rotation and the vector for translation separate. What's up with that?
Turns out there are some really practical reasons. First off, memory. A quaternion and a vector together is just 7 numbers. A 4x4 matrix is 16 numbers. That adds up. Second, they're a bit more robust. They're less likely to suffer from tiny little rounding errors that can build up and make a matrix, well, drift over time. And third, and this is a big one, it comes down to a really important idea for making robots move smoothly, interpolation.
So what the heck is interpolation? All it means is figuring out the in-between steps on a path. Think about this robotic arm. For it to get from point A to point B smoothly, you need to calculate a nice fluid path. Here's the catch. You can't just average 2 of those big 4x4 matrices to find the halfway point. The math just breaks. It doesn't give you a valid rotation. But you can do that with quaternions. You can smoothly blend from one to the other, and that's the secret sauce that makes this kind of graceful, predictable motion possible.
So it really all comes down to using the right tool for the right job. If you're doing a ton of super fast calculations, like figuring out all the joints in a robot arm, those 4x4 matrices are your best friend. They're built for that. But if you need to store a pose or send it in a message to another part of the robot, or especially if you're planning a smooth path, then the quaternion plus vector combo is way more robust and efficient. It's just the smarter choice for those tasks.
So there we have it. We've just given our robot all the mathematical tools it needs to finally answer that fundamental question, where am I and which way am I facing? It now has a solid mathematical model of itself within its world. But that just opens the door to the next giant question in robotics, doesn't it? Now that it can perceive its world, how does it decide what to do next?